At the moon's south pole, where dusk never quite ends, a quiet promise glows at the rim of shadow. Helium-3, both a hope and a provocation. We drift toward permanently shadowed craters, PSRs, where temperatures fall below -200 degrees and night has lasted for billions of years. From this darkness, we cut to Earth at night, a reminder of the fusion dream, star power on demand, clean energy without carbon or long-lived waste. Helium-3 is a rare isotope of helium delivered by the solar wind, alluring because its fusion could be mostly aneutronic, energy with far fewer stray neutrons. In 1986, thinkers like Gerald Kulczynski and others championed the idea of mining lunar helium-3, and a speculative turning point quietly entered policy memos. Fusion's road was already long. The Lawson criterion sketched the thresholds, then tokamaks caged plasmas, and lasers hammered pellets in bursts of brief hope. Under a desk lamp, Apollo sample trays told a quieter story. The moon's soil had trapped whispers of the sun across eons. On an airless world, micrometeoroids till the surface, and the solar wind implants helium-3 into tiny mineral grains over unimaginable spans of time. Over billions of years, surfaces mature differently. The dark maria gather more helium-3 than the bright highlands, simply by composition and exposure. Geology maps tie helium-3 to ilmenite-rich basalt plains, yet the South Pole, prized for ice and power, sits far from the richest deposits. But sunlight is scarce at the South Pole, so prospectors eye ridge crests for near-eternal power while scanning shadowed floors for pay dirt, a logistical split screen. Here's the catch. Helium-3 thrives in sunlit equatorial mare soils, while the South Pole's icy PSRs likely hold less. Abundance and accessibility pull in opposite directions. To even estimate yields, geologists turn to Apollo sample chemistry and regolith maturity indices, then extrapolate across terrains with hard margins of doubt. Helium-3 hides in nanometer-thin rims of mineral grains, especially ilmenite. Heating the soil to a few hundred degrees can drive it out, but at a staggering industrial scale. Early estimates dreamed big, tens of thousands of tons of helium-3 on the moon. Yet concentration is measured in parts per billion to parts per million, not a miner's fantasy. And the fusion side is harsher. Deuterium helium-3 requires far hotter plasmas than deuterium tritium, with poorer cross-sections and stubborn confinement demands. Advocates counter with aneutronic allure, less neutron damage, simpler shielding, direct electricity via charged particles, translating to lighter reactors in theory. Skeptics reply that even aneutronic isn't neutron-free, and Bremsstrahlung radiation could waste more energy than we gain. Physics bookkeeping that doesn't blink. Back on the moon, extraction means moving mountains, strip mining regolith, baking it in continuous kilns, and trucking spent soil, an industrial spine across razor-edged terrain. Powering that chain likely demands nuclear sources or vast sun-tracking arrays on peaks of almost eternal light, cabled down into the cold. Thermal math bites. To release parts per billion helium-3, regolith must be heated to roughly 700 to 900 degrees Celsius continuously, with losses clawing at every watt. Engineers sketch closed loops, capture boil-off, recycle heat with counterflow exchangers, and squeeze every joule before the cold void steals it away. But yield is merciless. 100 tons of soil might give grams of He3, demanding a logistics ballet measured in megatons over decades. If not the South Pole, some argue, target sunlit maria with richer ilmenite and then solve the different problem, heat rejection under relentless day. At the pole, however, the prize is water ice, propellant, life support, and shielding, an anchor resource helium-3 must negotiate with. Any mining plan becomes triage. Prioritize water, oxygen, and metals first, then decide whether helium-3 rides along as a trace co-product. Then there's separation chemistry. Helium slips through sieves, cryogenic traps, getters, and membranes must sort a whisper from a storm of other gases. Meanwhile on Earth, economists tap calculators, transport from moon to cislunar depots, then to reactors that do not yet exist, compounds risk upon risk. Their models whisper that any helium-3 market depends on fusion's timeline, a moving target with milestones, delays, and occasional leaps. Back at the pole, dust is the omnipresent antagonist, electrostatically clingy, abrasive, and hungry for seals, joints, and lungs. Engineers answer the dust with countermeasures, electrostatic brushes, sintered filters, and sacrificial seals, each fix adding mass, cost, and points of failure. Inside the habitat, a systems lead spreads a fault tree on a light board, tracing how one clogged valve could cascade through air, heat, and power. Risk officers run Monte Carlo sims, and the output is sobering. Timelines stretch, spare parts spike, and margins evaporate in the lunar vacuum. Meanwhile, spectrometers hum on rover masts, sweeping crater rims to map volatiles, water ice first, but helium-3 always in the margins. Their scans confirm the old suspicion. At the South Pole, helium-3 rides low. Geology and shadow have not been kind to this dream. So attention pivots to the Maria, ilmenite-rich basalt plains far from the pole, where helium-3 concentrations rise with ancient lava flows. But the Maria lack near-perpetual light and stable cold traps. Infrastructure must span scorching day and freezing night, doubling the burden. Logistics planners sketch an elegant compromise: mine richer soils at the Mare, process and ship to a polar depot powered by steady sunlight. On Earth, the fusion camp stays split. Tokamak builders ask for incremental wins, while Aneutronic advocates argue for a bolder lane change. They agree on one hard point: without high-temperature superconductors and robust RF heating, any helium-3 path is just ink on paper. Prototype teams pivot to field trials. Small HTS coils are trucked to a desert test site to prove they can run steady in grit, heat, and silence. Back on the moon, planners run simulations: a polar depot with sun-tracking arrays, cryotanks, and a docking pad stitched into the rim of Shackleton. A trade study lands hard. Helium-3 extraction wants Mare soils, but life support and power want polar light and water, two maps that barely overlap. Enter a third axis, risk, because hauling cryogens across vacuum, then landing on knife-edge ridges, multiplies failure modes nobody funds lightly. Meanwhile, China scouts the pole with Chang'e landers and orbiters, their instruments mapping illumination, temperature, and subtle soil signatures. India, Russia, Europe, and private outfits answer in parallel, an era of polar prospecting where every crater rim becomes a data point and a bet. Economists step in with sober math. If fusion slips decades, helium-3 revenue curves collapse, while water ice and communications may pay sooner. On the physics side, an old caveat reasserts itself. Deuterium helium-3 needs extreme temperatures and clean beams that punish imperfect machines. Still, a quieter promise forms. Instruments refined for helium-3 hunting also sharpen knowledge of the sun's wind and the moon's surface physics. The debate matures. Helium-3 shifts from silver bullet to strategic option, contingent on progress in both fusion cores and lunar logistics. So the question sharpens: is the lunar South Pole truly the best gateway for helium-3, or merely the best foothold for everything else we need to learn? Field data arrives in careful drips. China's Chang'e 4 and Yutu-2 hint at volatile traps, while India's Chandrayaan-1 and 2 refine polar maps that sketch opportunity with uncertainty. Yet, helium-3 is not a volatile. Its trail is locked in fine grains exposed to ancient sunlight, which the South Pole's eternal shadows rarely provide. This creates a split strategy: prospect where sunlight once baked the soil for helium-3, but stage operations at polar ridges where power and water ice sustain crews. In that plan, the South Pole becomes a logistics keystone: power farms on sunlit peaks, ice cracked to life support and propellant, and labs evaluating tiny vials of dust for isotopes. But the yield math is stubborn: kilograms of helium-3 per billion kilograms of soil, demanding industrial heaters, sieves, and days of bakeout to skim a whisper of gas. Economists enter with a cooler ledger. Every watt lifted off Earth, every gram refined on the moon, must compete with alternatives like terrestrial renewables and different fusion fuels. The counterpoint holds: if fusion cores mature to burn helium-3 cleanly, even sparse lunar supply could become strategic, like platinum in catalysts rather than coal in furnaces. So, the debate refines to a timeline. Can prospecting, pilot processing, and sample returns keep pace with advancing fusion, or will the need evaporate before the mines are ready? Outside, the city hums under sodium haze, reminding everyone that energy transitions are lived on the ground, meter by meter, bill by bill. Inside the late-night lab, the team drafts a sober plan. Small robotic scouts to map helium-3 proxies, sample return to ground truth, and only then talk of ore. They budget the hidden costs: cryogenic traps, vacuum ovens, dust mitigation, teleoperated drills, and compare them to a fusion timeline that refuses to wait. Outside funding rooms, the argument hardens. Is Lunar Helium-3 a research catalyst worth pursuing now, or a mirage distracting from nearer wins like grids and deuterium tritium? In the end, their proposal narrows to proof of knowledge. Measure actual helium-3 in returned grains from polar and equatorial sites, publish, and let reality lead. If the numbers come back modest, the dream doesn't die, it scales to science. A better solar history, better geology, and wiser bets for future engines. And if they return rich seams after all, the South Pole's cold silence will have an answer, patient, measurable, and finally earned by evidence.